Hi everyone, welcome to the next webinar in the LC series of Pheno Academy. This one will be all about measuring peak separation quality and specifically about resolution, asymmetry, selectivity, and efficiency. My name is Koen, I'm a technical specialist here at Phenomenex, and without any further ado, let's get started. Here's an outline of today's topics. First, I will talk to you about what quality of a chromatographic separation actually is and why we measure the quality. Next, I will take you through asymmetry, followed by efficiency, then selectivity and resolution, and I will conclude with a short summary. In the end, there will be time for a short Q&A session, so please do feel free to type your questions in the question box. And you will see the slide numbers indicated here as well, and you can find them in the bottom right corner of each slide, so that if you're reviewing this webinar, each section should be a little easier to find. All right, so first up, the quality of a chromatographic separation and why we measure it. So the goal of chromatography is just to separate analytes. That is all that chromatography is. It is separation science. Now, when we're talking about separation quality, it implies that high quality means a good separation and that low quality means a bad separation. But I just wanted to reinforce that if you get the results that you need from your chromatographic method and you keep getting the results that you need, your method is absolutely fine. So then, why do we measure asymmetry, selectivity, efficiency, and resolution? It is that so we get objective results, objective measurements, so that we can compare analyses. You could, for example, compare your analysis to one in a different lab, or you can use these measurements to improve your method during method development, or you can check how your method is performing compared to how it used to. So this also enables you to measure the consistency or the repeatability and reproducibility of your method, which is very important in validating the method and in system suitability testing, which happens a lot, for example, in the pharma QC testing area. To give you examples of those 4 separation quality attributes, I wanted to show you the CQA, the Certificate of Quality Assurance of an LC column. So you can see some of those attributes there at the bottom, like K factor and plates and asymmetry. And your LC system software usually calculates all of these for you, so you don't have to do that yourself. But if you know what goes into these calculations, then you know what happens in your chromatographic pathway of your analysis, which in turn helps you understand better like where to troubleshoot your method or how to optimize your method. That said, this webinar is not going to be in depth about troubleshooting or method development. There are going to be 2 webinars next in this LC series of Pheno Academy. So if you're interested, then please stay on the lookout for those. And for now, brace yourself. There are going to be a lot of formulas, a lot of calculations in this webinar, and we're going to see this CQA a lot more. The first of the 4 that we're going to cover is asymmetry. And I can't really cover asymmetry before going over diffusion. Here you see a purple sugar cube that is being dropped into water. Now, as you know, the sugar cube dissolves in water and the sugar molecules diffuse over the available volume until they are more or less equally distributed. Diffusion also happens in the chromatographic pathway. So here on the left, an analyte enters the pathway when a sample is injected. In the middle is the LC column, packed with these spherical particles. And then the analyte travels through the column and then onto the detector. And as you can see, the analyte diffuses along the way, and when it is detected, we get a peak. Now we are ready to talk about asymmetry, also called peak asymmetry or the symmetry factor. Because in an ideal world, every molecule of an analyte has exactly the same flow path through the chromatographic pathway, and it has the same interactions with the column stationary phase. So then every peak would be a perfectly symmetrical Gaussian peak. But we don't live in an ideal world, so even though we sometimes do see symmetrical peaks, they are usually skewed to some degree. So here is how asymmetry is calculated. You divide the width of the part after the apex of the peak, so part B, by the width of the part that comes before the apex, part A. This is commonly done at 10% of the peak height, but for example, in pharmacopoeia methods, 5% peak height is used. So then if you get a symmetry factor of 1, then you have a symmetrical peak. If you have a symmetry factor of more than 1, then you call that a tailing peak, and lower than 1, that is a fronting peak. And common asymmetry values are between 0.9 and 1.5. So here you see examples of fronting and tailing peaks. In a fronting peak, A is much larger than B, which means that part of the analyte takes less time to elute from the system. And with a tailing peak, B is larger than A. So that means that part of the analyte is retained more, or part of the analyte has taken a longer flow path. Now back to our CQA. Here you see the asymmetry factors of the peaks pointed out. And there is one symmetrical peak, but overall tailing peaks are more general, more common than fronting peaks. And what is a good symmetry factor really depends on what you need. As long as peaks don't co-elute or integration is otherwise problematic, then you are okay. However, the worse that peaks do front or tail, the broader they are, meaning that peaks could start overlapping, indicating that analytes are co-eluting, and that makes their quantitation less accurate. Our next parameter is efficiency. All that efficiency is a measure of diffusion. So peak width depends on diffusion. A lot of diffusion leads to wide peaks, making efficiency low. And little diffusion gets you sharp peaks, and sharp peaks mean high efficiency. You will hear a lot of band broadening effects that would lower efficiency. And it is very important to keep in mind that in chromatography, efficiency depends on the LC system setup as well as the column, and I will show you why later. So peak efficiency N is calculated by multiplying factor A, depending on where you measure the width of the peak, by the square of the retention time TR divided by the width of the peak. There is also column efficiency, which should arrive at the same number as peak efficiency. And column efficiency tells you how efficient a column can be. As you can see in the formula, column efficiency increases with column length and with smaller theoretical plate height. These theoretical plates, they are just a concept. Of course, there are no actual plates in LC columns, but the more of these theoretical plates there are in the column, and so the lower this plate height is, the higher the column efficiency. I wanted to emphasize just how important optimizing the LC system is in getting high efficiency. So we are going to compare two setups. Everything is the same analyte, same flow rate, same column, except that in the bottom setup, the tubing connecting the column to the detector is longer. Now, watch what happens to the analyte band. As you can see in the longer tubing, here we go, there is a lot more opportunity for diffusion to take place, so efficiency is decreased and the peak is broader. You could be the best chromatographer in the world with the most efficient column there is, but if you do not optimize your LC system, you basically undo a lot of the column's hard work, and you will never see the efficiency that you could be getting. To give you some reference efficiency values, here you see a table where you see the efficiencies of materials in theoretical plates per meter. So you can see that with decreasing particle size, efficiency increases, and also for core shell particles, the efficiency is higher than for fully porous. For our CQA column, we have a fully porous column with 5 micron particles, and it is 250 millimeter long, so that is 1/4 of a meter. And so if we multiply the plates that we are getting by 4, then we see that we do indeed get to around this 100,000 plates per meter number. There is much more about chromatographic efficiency than I can cover in this webinar, so if you're not tired of looking at formulas yet, I would recommend learning about mass transfer kinetics, which covers how fast analyte molecules interact with the stationary phase, and about Van Deemter curves, which relate the theoretical plate height of a column to the flow rate of the mobile phase. And in this image, you see less diffusion in core shell columns than in fully porous columns, which is why core shell materials can be more efficient. In this next part, I will cover selectivity. Before we can talk about selectivity, though, we need to talk about a retention factor. This is also called capacity factor or relative retention. And the retention factor is the retention time of an analyte, TR, relative to the time that unretained compounds, so T0, elute. So it is just to normalize retention, because the timescale on the x-axis here in the chromatogram, it only indicates how much time has passed after injection of the sample. By itself, it does not say how much an analyte is actually retained or if it is retained at all. So the unretained compound here is uracil, the first peak, and we call that the void marker. So we are going to calculate the retention factor of toluene. For that, we take the retention time of toluene minus the retention time of uracil and divide that by the retention time of uracil. And when we do that, we get to 1.8, which was indicated on the CQA as well. So on to selectivity, or the separation factor alpha. Selectivity indicates how far peaks are separated at their apices, so at their tops. It depends on the column stationary phase and on the composition of the mobile phase. So if you change these, then selectivity will change as well, which is important in method development. And selectivity really just means, is your method selective? So does the method allow you to tell apart one analyte from another? The way that selectivity is calculated, you see here in the formula, is that you take the retention factor of the latter peak and divide that by that of the former peak. And I wanted to show you that you do not have to do that for two adjacent peaks. You can calculate the separation factor for any two peaks. So here I took naphthalene and acetophenone. And then we can calculate by using their retention factors that the selectivity is 3.14. Moving on to the final of our 4 separation quality attributes, resolution. Resolution is really where many of the factors that we discussed before come together. So it is described by the Purnell equation, and you can see in the equation that resolution is a combination of efficiency, selectivity, and retention. And where selectivity measures the separation of peaks at their apices, Resolution measures the separation of peaks at their bases. Here you can see the impact of each of the three factors on resolution. So first about relative retention in green. Having at least some retention is important, of course, or else your analytes would elute in the void volume. But it quickly loses effectiveness in increasing resolution. So recommended is for relative retention to be between 2 and 10. As you can see, further increasing relative retention doesn't really increase resolution anymore. It just makes you having to wait longer until your analytes have eluted. Increasing efficiency increases resolution, but a little slowly. Because of that square root, if you manage to double your efficiency, then that means resolution increases by the square root of 2, so by about 1.4. And increasing the selectivity, so how your analytes behave depending on the stationary phase and the mobile phase, is simply the most effective. And lastly, you can see by the Purnell equation and by the graph that you need at least a little of each of the three factors in order to be able to resolve two peaks from each other. If any of these three factors is 0, then resolution is also 0. As I mentioned before, resolution describes the degree of baseline separation of peaks. And to demonstrate that, here you can see what increasing efficiency or increasing selectivity looks like. So when you start with insufficient resolution, you see these two peaks, they overlap, so analytes are co-eluting. If you increase efficiency, then you see that the peaks are sharper and they are still as far apart as they used to be, so selectivity hasn't changed, but now you have achieved baseline separation. Or when increasing selectivity, you can see that the peaks are still as broad as they used to be, so efficiency didn't change, but because the analytes elute further apart, there is also baseline separation. To calculate the resolution between two peaks, I changed the equation a little to indicate that you need to take the efficiency and the retention factor of the latter peak. You use the selectivity factor between the former and the latter peak. Again, the peaks don't have to be adjacent. You can calculate resolution between any two peaks, but a resolution between two adjacent peaks is often what is critical. So we will use two adjacent peaks here. For the resolution between the third and fourth peak, so toluene and naphthalene, we use the efficiency of the naphthalene peak, the selectivity factor between the two peaks, and the retention factor of naphthalene, and we arrive at a resolution of between these two peaks of 5.23. And that was it for resolution. So on the next slide, I will give you an overview with each of the 4 attributes that I covered today. To summarize, and starting at efficiency and going counterclockwise, asymmetry depends on interactions, and perfectly symmetrical peaks have asymmetry factor 1, fronting peaks have a factor of lower than 1, and tailing peaks have a factor larger than 1. Efficiency is a measure for peak width. It depends on diffusion. High efficiency means sharp peaks. Low efficiency means wide peaks. Selectivity is a measure of peak separation at their apices. It depends on the stationary phase and the mobile phase. And resolution is really baseline separation between two peaks. And this depends on efficiency, selectivity, and retention.